S parameters of an open-circuited stub are solved in this electromagnetic 3D harmonic analysis tutorial. The presence of an open stub results in an S parameter in which electromagnetic waves of a particular frequency are totally reflected and do not pass at all. As shown in the graph of the S parameter in the calculation result diagram, the open stub model in this tutorial shows the characteristics of total reflection near 6 GHz. A new project is created first. Create a new project. Click the File tab and select New Project. Set up the analysis space as follows. Set Model Unit mm. Set Analysis Space 3D. Click OK button. The initial setting has been done. We create a box for the substrate and another for the ambient air. On the Model tab, click Solid and select Box Specify Length on the submenu. Designate the start point. In the Parameter Input dialog box, enter start point x0, y0, z0, and click Next button. Set the width. Enter width 20 and click Next button. Set the depth. Enter depth 20 and click Next button. Set the height. Enter height 1 and click Complete button. Now the box for the substrate, SUB, has been created. Create another box for the ambient air. Designate the start point. In the Parameter Input dialog box, enter start point x0, y0, z1 and click Next button. Set the width. Enter width 20 and click Next button. Set the depth. Enter depth 20 and click Next button. Set the height. Enter height 6.4 and click Complete button. The box for the ambient air has been created. Click Exit button in the Parameter dialog box and exit. Two rectangles for the stub electrode are created. On the Model tab, click Sheet Body button and select Rectangle Specify Length. Designate the start point. In the Parameter Input dialog box, enter starting point x0, y0, z1 and click Next button. Set the width. Enter width 20 and click Next button. Set the height. Enter height 2 and click Complete button. A rectangle has been created. Create another rectangle for the open stub. Designate the start point. In the Parameter Input dialog box, enter starting point x10, y2, z1 and click Next button. Set the width. Enter width -2 and click Next button. Set the height. Enter height 6 and click Complete button. Click Exit button and exit the dialog box. Two rectangles have been created. We unite two rectangles in this session. On the Model tab, click Unite Boolean. In the Body tree, select both Body 2 and Body 3. Click Complete button in the Unite Boolean dialog box. Two rectangles have been united and Body 4 has been created in the Body tree. We move the stub electrode to the target location. On the Model tab, click Move. In the Body tree, select Body 4. Click Next button in the Parameter Input dialog box. Enter Move Vector x0, y7, z0 and click Complete button. Finally, click Exit button and exit from the dialog. Now the stub electrode is properly positioned. We set the analysis conditions. On the Model tab, click Analysis Condition. The Analysis Condition Setting dialog will show up. Select Electromagnetic Analysis Hertz on the Solver tab. Go to the Electromagnetic Analysis tab. Confirm that the analysis type is Harmonic Analysis. On the Harmonics Analysis tab, select or enter the following parameters. Sweep type, linear step by division number. Minimum frequency, 1 GHz. Maximum frequency, 10 GHz. Division number, 100. Next, click the Mesh tab. Set the reference frequency in frequency-dependent meshing, 5 GHz. Click OK button. The analysis conditions have been set. We assign names to the body attributes and the material properties. Highlight the substrate and click to select. On the right-click menu, select Body Attribute/Material Property. In the Body Attribute/Material Property Setting dialog box, enter Body Attribute Name, Sub, Material Name, Sub, and click Edit Date button. In the Edit Material Property dialog box, enter Relative Permittivity 5, and click OK button. Then click OK button in the Body Attribute/Material Property Setting dialog box and exit. Highlight the ambient air and click to select. On the right-click menu, select Body Attribute/Material Property. In the Body Attribute/Material Property Setting dialog box, enter Body Attribute Name, Air, Material Name, Air, and click OK button to exit. To select Strip Line Body, click Body 4 in the Body tree. On the right-click menu, select Body Attribute/Material Property. In the Body Attribute/Material Property Setting dialog box, enter Body Attribute Name, Electrode, Material Name, Electrode, and click Edit Date button. In the Edit Material Property Electrode dialog box, go to the Electric Conductivity tab. Enter electric conductivity 1 × 10⁷ power Siemens/meter. And click OK button. Then click OK button in the Body Attribute/Material Property Setting dialog box and exit. The body attributes and the material properties have been set. We set the port boundary conditions. The ports on Hertz are set on the area where the transmission line exists. Transmission line is the structure to carry electromagnetic waves. Parallel plates, microstrip lines, and waveguides are the transmission lines. The integral paths and the electric field directions are also set up here. On the Model tab, click Select Face on the drop-down list at Switch Object. Set up port_001 first. Highlight the face of the ambient air for port_001 and click to select. Also highlight the face of the substrate for port_001 while pressing the Control key and click to select. On the right-click menu, click Port. In the Port dialog box, the port name, port_001 will appear automatically. Just click OK button. In the Edit Boundary Condition port_001 dialog box, click Setting button. Set up the integral paths and the electric field directions on the ports. To snap the middle point of an edge, go to the Snap tab and enable middle point. Other snap commands may be disabled. Click the starting point on the modeling window. The starting point coordinate is X, 20, Y, 8, Z, 1. Next, to snap a point on edge, go to the Snap tab and enable Point on Edge. Click the endpoint on the modeling window. The endpoint coordinate is X, 20, Y, 8, Z, 0. In the Edit Boundary Condition port_001 dialog box, select Specify at Reference Impedance and click OK button. The integral path of port_001 is created. Set up port_002. Port_002 can be set up on the other side of the model in the same way as port_001. Highlight the face of the ambient air for port_002 and click to select. Also highlight the face of the substrate for port_002 while pressing the Control key and click to select. On the right-click menu, click Port. In the Port dialog box, the port name, port_002 will appear automatically. Just click OK button. In the Edit Boundary Condition port_002 dialog box, click Setting button. Set up the integral paths and the electric field directions on the ports. To snap the middle point of an edge, go to the Snap tab and enable Middle Point. Other snap commands may be disabled. Click the starting point on the modeling window. The starting point coordinate is x0, y8, z1. Next, to snap a point on edge, go to the Snap tab and enable Point on Edge. Click the endpoint on the modeling window. The endpoint coordinate is x0, y8, z0. In the Edit Boundary Condition port_002 dialog box, select Specify at Reference Impedance and click OK button. The integral path of port_002 is created. Let's check the Outer Boundary Condition setting. On the Model tab, click Outer Boundary Condition. In the Edit Boundary Condition dialog box, go to the Electric tab and confirm that the boundary condition type is electric wall. Then click OK button. Now the outer boundary condition is confirmed to be electric wall. Now, run the solver. On the Model tab, click Run Mesher/Solver. The calculation will start. Please wait for a while until the calculation is done. The Calculation Finished dialog box will show up when the calculation finishes. Select Fields and deselect Tables and click Show button. The screen will change to Results window, and the meshing result will show up. The calculation results are available in various format. Let's see the field vectors and some graphs and charts. Let's see the electric field vectors. On the Results tab, click Element Vector. The electric field vectors will show up. We can see how the electric field vector is distributed from the strip line to the surroundings. Next, let's see the magnetic field vectors. On the Results tab, select Magnetic Field in the Field pull-down. The magnetic field vectors will show up. We can see how the magnetic field vector is distributed around the strip line. Let's take a look at S parameters. On the Results tab, click Inverted Triangle button at the side of Show Characteristics chart. Click SYZ Matrix on the submenu. The SYZ Matrix dialog box will show up. Select both components 1,1 and 2,1 while pressing the Control key, and click XY Graph button. The frequency plots for S11 and S21 will be shown. This plot shows that the S11 is 0 dB near the frequency of 6 GHz, indicating total reflection. Let's see the Smith chart. In the SYZ Matrix dialog box, click Smith Chart button. Smith chart will appear. This Smith chart shows the amplitude and phase change of each component of the S parameter with respect to frequency. Next, let's animate and compare the electric field distribution at a frequency of 6.13 GHz, where total reflection occurs, and at 10 GHz, where little reflection occurs. In the mode pull-down, set the mode to 10 GHz, mode number 100. In the field pull-down, set the electric field vector and click Play Animate button. By setting the speed setting of the animation to high speed, you can better understand how the electric field propagates. At 10 GHz, you can see the electromagnetic field passing between the two ports. Stop the animation, change the mode to number 57, 6.13 GHz, and do the same animated display of the electric field vector. Then, unlike the 10 GHz case, there is resonance of the electromagnetic field in the open stub. This resonance shows that no electromagnetic field is passing between the two ports. This concludes our review of the results. Finally, save the project. Click the File tab and select Save Project As. Enter the file name and the location in the Save As dialog box, and save it. Saving allows you to launch Femtet at a later date, open the project, and review the model and analysis results. That's it for the Electromagnetic 3D Harmonic Analysis tutorial video. See the tutorial topics in the Femtet help for more information. Thank you for watching until the end.